Okay, so these next examples are going to look at what happens when we have a payment made during our investment or loan. So this example says Mr. Cheers wants to retire in 20 years, and for this purpose he is depositing $7,500 at the start of each year into a super account that is paying an interest of 6.9% per annum, compounded annually. If he will be doing this for 20 years, how much money will Mr. Cheers have when he retires at the end of the 20th year? So in order to show you the link back to sequences and series that are geometric, we're going to have a look at, well, what is happening every year. So at the moment we deposit things at the start of each year. Now that is crucial for this at the moment. We'll have a little look how that affects things. We also know we have an interest rate of 6.9%. We're compounding annually. We're going to be doing this for 20 years. And we're looking at how much do we have at that point, so what is the future value of this investment. So let's have a little think how this looks. The end of year one value. So what happened is you invest $7,500 at the start of the year. You add 6.9% interest, so 1.069 would be what you'd multiply by to find out that value. At the end of year two, let's have a little look at what would happen then. So at the end of year two, you would have the amount you started with at the end of year one. So you'd have your 7,500, I might use brackets rather than the times sign, times 1.069. And you would then be adding in an extra 7,500 at the start. And then at the end of this year, so at the end of year two, you would then have the interest earned on all of that. So you'd be multiplying it all by 1.069. If I just expand that, I can multiply everything inside this bracket by 1.6069. So I'm going to end up then with 7,500 times 1.069 squared plus 7,500 times 1.069. At the end of year three, we are going to have the amount we had at the end of year two, so that's going to be our 7,500 times our 1.69 squared plus our 7,500 times our 1.069. And then we're going to add into that, so I might use square brackets here, we're going to add into that an extra 7,500 at the start because we make a payment at the start of every year. And then at the end of this year, we're going to multiply all of this by our interest rate again. So what I'm going to do is I'm going to distribute that now to everything inside the bracket. So I'm going to multiply it into here, and into here. So end of year three, I'm going to get 7,500 times my 1.069 all cubed now. And this one's now going to be squared. And we're going to have our final value. So we can see a repeating pattern occurring here. We seem to be adding in an extra 7,500 and the powers are just increasing as the years go up. So we can predict now, based on this pattern, that at the end of year four we're going to have something that will be 7,500 times 1.069 to the power of 4 plus 7,500 times 1.069 cubed, and so on, all the way back down to just my 7,500 times 1.069. So this is going to keep occurring. So what we're getting here is we're actually, if I rewrite this back to front, we actually end up with a geometric series. So we have a first term of 7,500 times 1.069, and I'm then adding on another 7,500 times 1.069 squared, and from term to term we are multiplying by our interest rate every time, and this will keep happening up till the final term in your series. So we can see from here to here we have times by 1.069, and this will carry on, and you will sum all these values up till the nth term. So however many years you deposit this money. So what we can actually do mathematically is actually just convert this then to a series formula. So we know that Sn is equal to term 1 multiplied by r to the n take 1, all divided by r take 1. And in this case, what we know is our term 1 is equal to 7,500 times 1.069. Our r value is 1.069, and our n in this case was 20 years, because that's how long he was doing this for, Mr. Tuers. So if we find the sum of 20 terms, it will be T1, so that's our 7,500, 1.069, all multiplied by 1.069 to the power of 20, take away 1, all divided by 1.069, take 1. And if we type that in on our calculator, so let's go to run matrix. We have got 7,500 multiplying it by 1.069, then multiplying that by 1.069 to the power of 20, and then we're subtracting 1, and then all divided by 1.069 subtract 1 equals. And we get that he will accumulate 325,000 and $114.56. So that would be the amount. And doing it this way is a fairly laborious process. It takes quite a long time, and luckily enough, your calculator will do this on that financial mode fairly quickly. So let's have a little check to see how we get there. If we go to our financial mode, we go to F2 still. We're always going to be working through F2. And in this case, our number of years is going to be 20. Our interest rate is 6.9%, so there's nothing crazy happening just yet. Our present value, now that's how much you start with. Well, he doesn't start with anything, so at the moment that would be a 0. Our payments, so that's how much we are going to pay into this account. And because we're paying it into a savings account, it's no longer ours, we're paying it out, we're going to write negative 7,500. Future value is what we want to find, so just leave that with any value in. And our per year and compounding year periods are 1, because we're doing it annually and it's per annum. Now, this one up the top here tells you when you make your payments, and at the moment we're assuming that our payments are being made at the end of the year, and that is not the case. Our payments are made at the start. So we need to change this. To do that, we press Shift Options. Shift Setup even, Shift Menu. And we change this from end to beginning. So here we go, beginning. And let's just hit Enter. So now it says beginning at the top there. We actually want to then find what is the future value of this. So if we now press FV, we can see we get that same answer of $325 and $114. $325,000, $114 and 56 cents, and we can see that down here as our value. Okay, so moving on to the next example then. So this example, a little bit different. We have, in this case, we are told a man has a substantial amount of money saved. Daniel is considering to buy a house, given that he's saved this money. He has had some substantial raises, he has redone his money plan, and has determined that after allowing for rates, repairs and maintenance, and assuming that he earns some income by renting rooms in his house to friends, he can afford $750 per month in house repayments. The current loan rate for housing loans is 8% per annum, and it is compounded monthly. He wishes to take out a 30-year loan to keep the repayments as low as possible. What is the most expensive house that Daniel can purchase? So, we need to have a little think about what we're looking at here, and we're going to do this using our calculator. So, n is our term, and it's the number of that we're going over. So in this case, because it's going to be 30 years, but we're compounding in months, the periods that we have is going to be 30 times 12, which is 360. So our n value will be 360. Our I value should be fairly easy to find, and that is at 8%. So we have 8% here, and we're using our 30-year section here. we know we're going to pay $750 per month, so that's our payments that we make. Now, just to be crucial, payments with housing loans are made at the end of each month. So we need to make sure that our payment is happening at the end. So when we look at that calculator, we need to move it from beginning to end. So our present value, well, that's how much the house is going to be worth. So that's basically at the moment, how much can he borrow? So that actually is our question. That's what we want to know. Our payments are going to be equal to $750. So because we're paying them, they're leaving our account. And obviously, at the future value of this loan, if he's paying off a housing loan, the future value would be 0. We don't want him to have anything left on this loan at the end. And our per year and compounding is 12. So we're going to change that into 12 and 12. So let's have a little look then at what this comes out as. So our n is going to be 30 times 12, which is 360. I is going to be 8. Present value we don't know, so you can leave it at 0. This will be negative 750. And then our future value is going to be 0. Per year is going to be 12. So working this out then, we want to find our present value. So our present value is actually going to be $102,894. So that is the amount that he is able to borrow given this situation. But at the moment, I've just realised I've not changed my setting to n, so I need to change that one first. So we're going to press Shift, Setup, change it from beginning to end, F2, and let's just double check this will actually change the value. So our present value is $102,212.62. So remembering that crucial thing, we need to make sure we change that. And our present value then is going to be $102,212.62. Okay, going to this question, last question. It says Sophie borrows $40,000 and repays $4,500 at the end of each year. We want to then say, okay, interest is of 8% per annum is charged on the unpaid debt. How much does Sophie owe after the 6th repayment? So this one on your calculator then is going to be fairly easy to run through. Our n value is going to be the number of repayments. So this one we're looking at the 6th repayment. So we're going to let this equal to 6. We are then going to say our interest rate in this case was 8%. So we'll leave that on 8. The present value of the loan, well, she borrowed $40,000, so she actually has $40,000 in her account, so that's going to be positive $40,000. She's going to repay $4,500 at the end of each year, so crucially that's now already on end, so that's good. So we're going to put in here $4,500 because she's going to pay that. Now because she's paying it, we need to actually make sure this also has a negative at the start because it's going out from her account. And we also know that this is just going to be happening on a yearly basis, just per annum, and it's just charged yearly. So we want those extra values down here to just be 12 and 12. 1 and 1 for years. At this point then, our future value is going to be what we need to calculate. So how much does Sophie owe after the 6th repayment? So pressing FV on here, we can see our future value then is going to be $30,463.29. So Sophie's going to owe that money. And obviously you would just state what you've done. So you would have your N equaling to 6, I equaling to 8, present value equaling to positive 40,000, payments, we pay out negative 4,500, future value is what we want to find, and our per year and compounding are both going to be 1, and then we find our future value comes out as $30,463.29. So let's now look at why this is the case then. We have a situation where we borrow 40,000 and repay 4,500 at the end of each year, and the interest is charged. So what happens is that at the end of year one, we start with a balance of $40,000, and then we are going to repay some of that money. So we get 40,000, we have interest charged on that account, so that's 1.08 because it was 8%. And then what we're doing is, after we've been charged the 8%, because that was on the balance for the year, we then repay $4,500 at the end of the year. So that's why it comes off afterwards, not before the interest is applied. At the end of year two, we're then going to have a situation where we have our end of year one amount. So that would be our 40,000 times our 1.08 and subtracting our first repayment. And at the end of year two, that value we had, we're going to apply the interest rate to that of 1.08%, and then we're also going to pay off another chunk of this. So we remove another $4,500. And if I distribute this 1.08 to everything inside the bracket in here, we can see we're going to end up with something that looks like 40,000 multiplied by our 1.08 squared minus 4,500 times our 1.08 minus 4,500. At the end of year three, let's see what happens with this pattern. We're going to take our year two value, so that is our 40,000 times our 1.08 squared minus 4,500 times our 1.08 minus our 4,500, and we are going to apply the interest to this, and then we are going to make a repayment at the end of the year. Applying and distributing that 1.08 to everything inside the bracket, I end up with 40,000 times 1.08 cubed minus 4,500 08 squared. And we can see there's a pattern occurring here again. So what we can do is we can actually rewrite this. So let's say we're looking obviously for the end of year 6 value. Our end of year 6 will actually, if we use this pattern, will be 40,000 times our 1.08 to the power of 6 minus 4,500 times our 1.08 to the power of 5 minus, and we're going to keep minusing all the way down to our $4,500. And you can see there is a pattern here, and it mainly occurs with just these 4,000, well, it only occurs with these 4,500s. So what is actually happening here is we are actually doing 40,000 times 1.08 to the power of 6 minus, if I pull the negatives out from all of this, it would become 4,500. If I rewrite these back to front, so I start with the one without a 1.0 on and 0.8 on and carry one back up, it would be 4,500 plus 4,500 times 1.08 plus, and we would keep adding these up until I get to 4,500 times 1.08 to the power of 5 when I'm looking at the sum to 6. So we can rewrite this then as 40,000 times 1.08 to the power of 6 minus the sum of the first 6 terms of this sequence. And in this case, to find s of 6, then we know s of n is equal to term 1 times r to the n take 1 over r take 1. And term 1 in this case is going to be 4,500. Our r is 1.08, and our n, because we're looking at 6 years, is 6. So we're going to get 40,000 times 1.08 to the power of 6 minus 4,500 times 1.08 to the power of 6 take 1 all over 1.08 take 1. And if we type that in on a calculator, we will get the same answer as this 30,463. So if we go back to here, we're going to do 40,000 to the power of 6 minus 4,500 all over 1.08 take 1. We can see we get the exact same answer, the $30,463.29. So we get the exact same answer of $30,463.29. The final thing then to have a little look at is part B, and we can do this again using the maths or just by subbing this into the calculator. So let's use the calculator. So if we go down to our financial mode, go to compound interest, we are now looking at how long does it take for Sophie to pay off the loan, which means our future value now needs to be 0, and our n is what we want to find. So if I type all this in, so n doesn't matter what's in there, I is still going to be 8, present value is 40,000, payments are 4,500, future value will be 0, and we're compounding yearly. I solve for n f1, we can see this is saying it takes 16.13, and this is in years, that's the time period we're working on. So it will take a total, so we can see for part B, let's write them over here. We can see for part B that n is going to be approximately 16.13 years, so therefore it will take 17 years to repay the loan under these terms. Mathematically, the way you can actually solve this is just to set the value of the loan, so this formula here of this 40,000 times this, take away this, if we actually just said, okay, well, to work out any value, so year n would actually be equal to 40,000 times 1.08 to the power of n minus the sum of n, that's what we would do. And so to find this, we want yn to actually end up being 0, that's what we want to be the value. So I get 0 equals 40,000 times 1.08 to the power of n minus, and my sum will be 4,500 times 1.08 to the n take 1, all over 1.08 take 1. And you can solve that on your calculator and get the same answer of 16.13. And that is everything.